Hello everyone, and thank you for joining. My name is François Gutmann. I'm a GPU dev tech at AMD, and despite the lack of description on this slide, I will be talking obviously about GPU hardware and occupancy. I thought the title was long enough already. So before we start, just a quick commercial break for GPU Open, which is basically a developer portal for everything CPU, GPU related, specifically for gaming, but for other stuff as well. At AMD, on here you can expect to find performance guides. You can also expect to find developer tools like the Radeon GPU Profiler or the Radeon GPU Analyzer that we'll be using in this talk. You can also expect to find our open source technologies like the FidelityFX SDK, FSR of course, and so you'll get the documentation and the code and so on. But you can also find blog posts, including this one, which inspired this talk. So if afterwards you want to revisit the subject in a more written form, please feel free to go check it out. Commercial break over, let's get right into it. So this is a screenshot of the Radeon GPU Profiler. And if you look at what's in the blue box, that's occupancy, plotted in blue, in green, and in yellow. And if you don't already know what it is, it's probably not super clear what is going on here. And actually, even if I gave you a definition of occupancy right away, it probably wouldn't be that helpful. And that is because occupancy is a fairly complex metric that is deeply tied to the hardware, as opposed to something like the FPS, where the higher the better, right? So the idea with this talk is that I first spend some time explaining the hardware so that it hopefully makes more sense, and then we'll look into occupancy itself. And hopefully, by the end of this talk, you'll be able to understand the slide and actually use the Radeon GPU Profiler to analyze your own workloads. So let's start with the hardware. And to introduce the hardware, I would like to piggyback on something that you hopefully know a bit better, which is the software. So if you've already programmed a GPU or if you use the graphics API, you've probably seen this view of the logical graphics pipeline, right? It's a bunch of steps that are applied one after the other. Some are fixed function, like the input assembler, the rasterizer, and the output merger, while some others are programmable, like here the vertex shader, the pixel shader, and many, many other stages that I haven't mentioned here, including the one and only compute shader all alone in its own pipeline. If we take a quick look at what this would look like on the hardware, and this is very much simplified, we would represent it a bit differently. So we still see a bunch of stages, but they're not this time applied one after the other. It kind of depends on what kind of workload you are running. So here we have different paths, like a vertex path in green, a fragment path in blue, and a compute path in yellow. If you look at some stages like the geometry engine here, it is only used by the vertex path. But if you look at the shader processor input, which I'll probably call SPI, and the workgroup processor, which I'll call the WGP, and which is also called the double compute unit sometimes, the dual compute unit sometimes, you can see that all of the paths use them. And it turns out that those are the two most important blocks for this talk, so that's just perfect. So before we just dive into those, I want to give you an overview of what a GPU is. So I want to give you an intuition as to how wide it is and how deep it is. So if we look at this diagram, so this is a very top-level diagram, we can already see that there are multiple blocks. Some are kind of unique, and some are replicated. So if we look at this gray one here, the front end, we can already see that there's only one instance of it for the entire GPU. And this is like the brain of the GPU. This is the thing that receives command from the CPU, parses them, and programs the rest of the GPU to execute your workloads. We can also see two yellow blocks, the L2 cache and the MOL cache, which stands for memory attached last level of cache. By the way, all the yellow blocks in those diagrams, they're either related to caches or memory. And so those two are, again, common to all the GPU. So if you're writing to it from any part of the GPU, any other part of the GPU is also able to see it. It is coherent. Of course, you don't have any way to say, hey, I want to write to L2 from HLSL, but if you're using instructions like atomics or globally coherent, for instance, it has to resolve at least to L2. And then we can also see that we have a block that is replicated 6 times here, a shader engine, which is basically a mini GPU. And before we dive into this shader engine block, I want to mention that all those diagrams and all the numbers that I will mention in this talk, they're about our 7900 XTX GPU, so it's the big Navi 3 or RDNA 3 GPU. All right, so what is a shader engine? A shader engine is itself made of many blocks, and it's a bit scary, but fortunately we can already realize that it is made of two shader arrays, so I will hide one right away. So the gray block on the right side is exactly the same as the different blocks on the left side. And so a shader array, we can already see that there is a yellow block, the L1 cache, and so each shader array has its own L1 cache. So if the shader array on the left writes to its own L1, the shader array on the right can't see it. There is no coherency protocol, and this is why we have to use barriers and be very careful with those. A shader array is also made out of 4 other blocks, the WGPs. So if you remember the hardware diagram from before, this is one of the most important blocks that we'll be talking about. And if you look at the top of the shader engine, we have a block that is instantiated only once, and this is the SPI, the other block that we mentioned before. It's also called the wavefront launcher here, so if you already know what a wavefront is, this is a bit of a foreshadowing. But if you don't know, don't worry, I'll get to it. So we're about to deep dive into a WGP, and this is going to be very scary. So take a deep breath, and don't worry, we'll get through it. This is a WGP. There's a lot happening here, but again, don't worry, a lot of it is replicated. So right from the get-go, we can see that there are 2 compute units, so I'm going to be hiding the first one at the top. Again, it's the same as the bottom part. And in the CU, we can also see that the SALU block and the VALU blocks are replicated, so I'm going to hide one of each and call the whole thing a SIMD. So this is already a lot more manageable. So what do we have in a workgroup processor? We have a bunch of yellow blocks again, a constant cache to, well, cache things coming from constant buffers, for instance. We also have an instruction cache to, well, again, cache instructions for your shaders. And we've got the local data share, which I'll probably call the LDS as well. And this is a block of memory that is used by threads within a compute shader that want to share memory. So, you know, in a thread group, all the threads can share some memory, so this is going to be stored here. And we can also see that in a compute unit, there is an L0 cache. So again, this is incoherent with the L0 cache from other compute units and other shader arrays and the rest of the GPU. We have also a texture unit, which is used to do addressing, filtering, and so on. And finally, we have the SIMDs that we'll look at in a second. But for now, that's already a lot of information. So if there are a few things that I want you to remember from this like short introduction to the hardware, is that it is very wide. So we've seen that the SIMD that sits at the bottom, there are 2 of them per compute unit. 2 compute unit per WGP, 4 WGP per SA, 2 SA per SE, and up to 6 SE per GPU. So that is very wide. It is also very deep. The L0 that sits at the very bottom of the GPU, the whole hierarchy goes through L0, L1, L2, mol, and finally memory. So if you're trying to fetch data from memory, it is likely, or it is possible that it will take a while to come back. And finally, we mentioned that there is something called the SPI, once per shader engine, and that thing is not replicated that many times, and it's the thing that launches wavefront. So again, I'll come back to that if you don't know what it is. Let's go back to the software side of things for a second. So if you've programmed compute shaders, you probably know that the API looks something like this. You ask the GPU to execute thread groups, and you usually call something like dispatch, which has 3 parameters, A, B, and C, to dispatch A times B times C thread groups. Here I have represented them as slices, so a slice is A times B thread groups, and then there are C slices for a total of A times B times C thread groups. But a thread group is itself, shockingly, a group of threads, and usually you declare them in 3 dimensions as well, using a decoration like num threads in HLSL, for instance, and so you have, again, D times E times F threads. In practice, the GPU will slice those workloads again into groups of threads that execute together. And those are the infamous wavefronts that I've been mentioning so far. On AMD hardware, a wavefront is either 32 or 64 threads. For the remaining of this presentation, I will be mostly pretending that there are always 32 threads, mostly because things work mostly the same, and because the actual differences between wave 32 and wave 64 could be an entire talk, so for another time. So let's look at the execution of a simple shader. This is a compute shader that has a thread group size of 32. This is not a good idea, this is just for the example. It takes a thread index as input, and it does a very simple piece of code. It initializes sum at 0, and then it tests the thread index, and if it's lesser than 16, it will add 1. If it's greater than 16, it will add 2, and then it stores the thing to memory. So you've probably heard that wavefronts, they're executed in lockstep, meaning that they all execute the same code, but they can execute it on different data. This is where the SIMD part comes from. It is a single instruction, but on multiple data. So in this slide, I have represented each thread by one of those red rectangles. And when you see a rectangle, it means that the thread is active. So at the beginning of the shader code, we have all threads running, and they all initialize their own copy of sum. They all store 0 in their own copy of sum. And when we talk about lockstep, usually the first question that comes to mind is, yes, okay, but what happens when not all the threads want to take the same condition? Well, usually we represent it that way. Some threads are active, and some threads are made inactive through an execution mask. In practice, they just don't have any side effects, right? The threads that don't execute the code, they won't touch their own copy of sum. So in this case, the first 16 threads, they take the condition, they add 1 to their own copy of sum, and the other ones don't do anything. And then afterwards, we inverse the execution mask, and the other 16 threads add 2 to their own copy of sum. And in the end, when we want to store everything to memory, we'll have 16 ones and 16 twos. So that's a very software view of the thing, but how does that actually work on the hardware? We'll take a very similar example, but slightly modified so that I can talk about more units from the GPU. In this case, the main difference is that we have a constant buffer which contains a single int called data, and the operations that we do in the shader are slightly different. The first instruction, though, it's the same as the previous one, right? We have a bunch of threads, and they will all initialize their own copy of sum with 0. We have to store this thing somewhere. And so if we look back at the VALU and SALU blocks that I hid under a SIMD box earlier, we can see that there is something called a vector general purpose register, or VGPR, which is exactly that. It is a bank of registers that is able to store 32 copies of the same thing. So this is great. We want to store something 32 times, so here we go. We pick a VGPR. And then in the next instruction, when we want to add thread index to sum, we are trying to actually add 2 VGPRs together. The thread index is also unique per threads, right? Like the thread 0 has 0, thread 1 has 1, and so on and so forth. To do this, we have a unit called the core MAC for multiply accumulate unit, which is able to take 2 VGPR and add them together. It will not do each copy of the value, it will not do addition on each copy of the value one after the other. It will do 32 of them at the same time. This is why I've written that it is 32 wide. And this is, again, where the SIMD part comes from, right? It is able to do 32 operations at the same time. But what happens if we have a data that is common to all the threads? Do we really want to store it 32 times? For instance, this data constant buffer. When we load it from memory, we actually want to store it in a scalar general purpose register. So this is, again, a register, but it's not replicated 32 times this time, but just once. If we want to add it to a VGPR, that's also possible through our core MAC unit. It is able to take an SGPR and a VGPR as input and store the result in a VGPR in a single cycle. That's fine. And then finally, we can, again, upload the result to memory. So that gives you some idea of some of those units that we have in the SIMD, but we haven't mentioned all of those, and that's mostly because it's hard to come up with an example that would cover everything. So we also have something here called the side MAC, which is also 32 wide. So it's a different execution unit. It has a bunch of instructions that are slightly different from the core MAC, but basically it's the same idea. We also have a transcendental unit. I don't know if you can read it, but it says 8 wide. So if you've ever heard that trigonometric operations are slow on the GPU, this is one of the reasons why. It's just not as wide as the other one. We usually say that it is quarter rate because it is 4 times as small as the Core Mac. And we also have a double precision unit, which is 2 wide, so it's even slower. And I think our friends at Epic have noticed. There's also a scalar ALU unit, which is able to run operations on scalar GPRs. And you might be wondering, okay, we have a GPU. The goal is to have a wide thing, a SIMD, so why do we have this unit that is able to execute on a single value? It can be useful when you're running a loop, for instance. So say you have a loop in a shader, and all the 32 threads will run through the same number of iterations. Well, you could offload that to the scalar ALU. And it is very interesting because the GPU is actually able to schedule operations on multiple of those units at the same time. So you could say at 1 clock, you could schedule a vector operation and a scalar operation. All right, I think that's all I wanted to say. So far, we have mentioned that the GPU splits workloads in wavefronts. We have mentioned that they execute on the SIMD. But we so far have only mentioned that a SIMD can execute a single wavefront. In practice, you can actually assign multiple wavefronts to a SIMD. On RDNA 1, we had 20 slots, and since RDNA 2 and onwards, we actually have 16 slots. And the very important part about this is that those waves assigned to a SIMD, they don't have to be executed in order, and they don't have to be executed in one go. This is very important, so I'm going to repeat it in a different way. So the wavefront, they don't have to be executed in order, and they can stop their execution and resume at any time. So in practice, the GPU can say, oh, I'm going to take one wavefront, execute it on the SIMD, stop it, take another one, and then stop it again, resume, and so on and so forth. So we'll take an example so that it's a bit clearer, I hope. In this example, I've picked only 2 wavefronts, so we'll only represent 2 wave slots, but this is a single SIMD, right? So the first wavefront starts executing some code on the SIMD. It does some ALU work until at some point it reaches a memory operation. So it says, hey, I need some data from memory. But as I mentioned before, the GPU is fairly deep, especially the cache hierarchy. And so we have no idea when the data will come back. So what we could do is just stall and wait for the memory to come back. Or, because we know we have different wavefronts and we know that we can switch them on the fly, maybe it's a better idea to actually switch to wavefront B. And if we're lucky, wavefront B has some ALU work to do. Turns out, because I made the example, wavefront B has a lot of ALU to do, and so it goes brrr for a while until the memory becomes available for the slot A, but wavefront B doesn't care, it keeps going until it also hits a memory operation, and we can again choose to either stall or maybe switch to a different wavefront. And since it turns out that wavefront A has its data back, we can switch back to A and keep executing that one. So what happened here is that we have hidden latency. While wavefront A had to wait for data to come back. In practice, since we were able to execute some other workload on the same SIMD at the same time, we completely hid that latency. It's like it never existed. If I want to say it differently, if we stop thinking about like slots and wavefronts on the SIMD, at every clock on that SIMD, there was an operation running on the SIMD. So we managed to reach 100% utilization of the SIMD. A quick detour through our tools. This is a view from the Radeon GPU profiler again. This time we are in the instruction timing tab on the bottom here. So if you click on this tab, you will see on the left side the ISA, so the assembly instructions that are executed by the GPU. And on the right side, you will see a latency column. So if you look here, there's a huge bar, and I don't know if you can read it, but here it says 8 million clocks latency. It turns out that the instruction that this refers to is a wait instruction, so it's not really surprising. What is interesting, though, is that this bar has two colors. There's a green part and a red part. And the green part actually shows you how much of that latency was hidden by other vector operations. And so in this case, we were able to hide about, I don't know, 80% of that workload, or of that latency, which is pretty good. And I don't know if you can see it actually on the screen. Yes, you can, I think. So on the left side of the bar, there's even a yellow cross-hatched section, which actually tells you how much of that latency was hidden by scalar operations. And the first time I saw this, I was like, this is a bit weird. How come the scalar and the vector, they just don't compound? Like, we should be able to hide more latency. But as I mentioned before, since the GPU is able to schedule scalar and vector operations at the same time, they actually execute in parallel, and so they hide the same latency. They don't add up. Another interesting thing that we have on this page is this histogram view. It shows you a repartition of the length it took to execute a wavefront. So you can see if your wavefronts were mostly fast or mostly slow, and you can actually move that slider around here to select a specific subregion. So you could say, oh, I want to investigate why those specific wavefronts go super fast or why those ones are really slow. And it will update this bottom view in real time. So we are now finally able to give a definition of occupancy. Occupancy is the ratio of assigned wavefronts to the maximum available slots. I don't really like this definition. Like it's not super clear to me, but in practice, it's really simple, right? Like you have 16 slots, and if you are able to fill four slots out of 16, that's 25% occupancy. And if you have 12 wavefront assigned, then that's 75% occupancy. A different way to think of this is if you have a single wavefront assigned to a SIMD, it doesn't give the GPU any chance to hide the latency, because if it's stalled waiting for data to come back from memory, then there's nothing else to switch to. On the other side of the spectrum, if you have 16 wavefronts assigned, then you have all the chances in the world to hide the latency through that mechanism. So let's try to get some intuition about occupancy. When is it good, and what it is not. So for instance, something that we often hear is that better occupancy means better performance. But in practice, that's not true. Say you have a workload that uses a lot of ALU work or does mostly ALU work. There's no point in adding another wavefront, right? Because the wavefront doesn't install waiting for data to come back from memory. So if you add another wavefront, there's no reason to switch to it. What might benefit from increased occupancy is a workload like this one, where you have to wait for the data to come back, and hopefully another wavefront can execute some ALU work. Occupancy can actually even be harmful, especially in a memory-bound scenario. In this example, I have represented 4 different wave slots. So the first one starts executing some ALU work until it hits a memory operation, so switch to a different one. It does the same thing, some ALU, and then a memory, and so on and so on. In practice, those waves, when switching to them, they basically hide no latency at all because they do so few ALU instructions. What they do instead is hammer the memory system with many memory requests. So the more you increase the occupancy, the more memory requests you'll fire. And in the end, it might end up thrashing the caches and evicting data that you would actually need for some other operations. Okay, so far we have mentioned occupancy mostly as an internal scheduling mechanism. And I told you it can be 25% or 65%, but we haven't really mentioned why or how. So if we take a quick look at this example that we've looked at before and compile it through, say, RGA, we'll get this. This is the assembly. And again, it's scary, but we can look at 2 interesting things here. There's an SGPR count and a VGPR count. This means that at compile time, we are already able to know how many resources are required to execute that shader. And if you recall, the goal of switching between different wavefronts is to hide latency. But this mechanism, it has to be really efficient. Say, if the overhead of switching to a different wavefront was higher than the latency you were trying to hide, that wouldn't be worth it. So this mechanism, it has to be really, really quick. And for it to be really, really quick, we want the GPU to reserve for each wavefront its own resources. So here, if we want to assign this wavefront to a SIMD, the SIMD first has to say, hey, I have 8 VGPRs free, otherwise it's not possible. And that way, at runtime, when switching from a wavefront to another, we don't have to do a bunch of copies everywhere. What we can say is just, oh, wavefront A using this range of VGPRs, and then wavefront B is using that as a range. And so an interesting thing of this, an interesting property of this is that at compile time, you can already get an upper bound on the maximum occupancy that you are likely to achieve. Let's say this shader required 150 VGPRs because the bank of VGPR is not unlimited. It's very unlikely that you can schedule 16 waves, right? Here we mention SGPRs as well, but in practice, this is basically free. We assign 128 of those per wavefront, and I've never seen a workload that ran out of those. One other thing that I want to mention regarding VGPRs is that the granularity at which they're allocated is not one, and the rules are a bit complicated. It depends on the GPU, and it also depends on the wave size, which is good, because we also see that at compile time. So far, I've mentioned that it can be either 32 or 64, and I've said, 32 works. Well, in this case, 64 is a bit different. If you remember, the SIMD is 32 wide, and the VGPRs, they hold 32 copies of a single value. So in wave 64, when executing 64 threads in lockstep, we need to be able to store 64 copies of the same value. So whenever a shader executes in wave 64, when it requires 1 VGPR, well, it really needs 2. So this is an important detail to keep in mind. Another thing interesting was, we can look at, again, the GPU profiler, the Radeon GPU profiler. In the Overview tab, we have all the resources that are available per SIMD, including the VGPR count, which is 1,536. So if we are trying to calculate how many VGPRs are available per wave in the different wave mode, we can divide that number by 16, and we get 96 for wave 32. But in wave 64, since we need twice as many VGPRs, that's only 48 VGPRs if you want to reach the maximum occupancy. So wave mode is very important when computing that value. Of course, you could do that manually all the time. That's possible, but it's also very annoying. So fortunately, we've automated this in the Radeon GPU profiler again. This time in the pipeline state tab, you will see the wavefront mode, you will see the number of VGPRs allocated, and we will also give you a hint as to what you can do to improve your occupancy. So here, for instance, it says, I don't know if you can read it, but it says the shader could potentially run 10 wavefronts out of 16. However, if you reduce the register usage by 12, you could run another wavefront. Boom, no need to run the computation yourself. However, you might say, okay, sure, I could reduce by 12, but how do I find out where or something like this? Well, we also have something for this, and this is actually quite new, and I'm really happy about it. In the instruction timing tab, you have some kind of a small hamburger menu here, and if you click on it, it says open the Radeon GPU analyzer, and you'll get this window. So in this window, again, on the left side, you will have the ISA. And on the right side, you will have the register liveness analysis. So it basically tells you per line how many VGPRs needs to be kept alive. And so we can see, for instance, that this line, it says 58, 59, so on 60, and then 61. And you can see that there are kind of two colors here. There's a green part of it, and then there's an empty blank space afterwards. This is what I mentioned was VGPR allocation granularity. We don't allocate one by one. And in this case, if we look at the top here, it says we used 61, but we allocated 72. So the granularity here is 12. And it's a bit of a shame because at maximum, when we require the most VGPR, it's only 61. So when you see this, you might want to try to go back to the HCL cell, shuffle things around, maybe try to use some value that needed to be kept around earlier so that it doesn't need to exist here, shave off one VGPR, and then move back to an allocation of 60 and improve your occupancy. For the record, this was a very optimized shader, and it took me a while to break it. That was very annoying. Another resource that you have to be very careful when running compute shaders is local data share. The same way as the VGPR, at compile time, we already know how much LDS you'll need, and it is not infinite. So if you require too much of that, of this resource, you will likely limit your occupancy. But with compute shader, there's something extra on top to think about, is that this LDS, it is memory that is shared by all the threads from a thread group, which means a thread group has to be assigned to a unit on the GPU that sees the same LDS. And that thing is a workgroup processor. Another important implication of this is that you cannot assign half a thread group to a WGP. So if you have a big thread group that uses 60% of the overall resources available on the WGP, there is no way you can assign a second one because you need to reserve in advance all the resources required for an entire thread group to schedule it. And so in this case, it would be very shameful, right? Because you have a lot of resources available, and you could schedule many more waves. But in practice, since you need to schedule all the waves from the thread group, it wouldn't be possible. So that's another thing that you need to care for when looking at occupancy of compute shaders. So back to this first slide. Hopefully, it now makes a little more sense. If we look again at the blue box at the top, in green, we plot the occupancy of vertex shaders, in blue of fragment shaders, and in yellow of compute shaders. And this time, it is not theoretical or maximum achievable occupancy, but it is occupancy that was actually measured on the GPU. And immediately, when looking at this, this workload, for instance, you might be thinking, oh, it doesn't look like it's super high. Maybe we could look into that. So what you can do is go to the timeline tab at the bottom here, click on the item, and it will open the panel on the right. Here we can look at the compute shader stage and see that the occupancy is actually 16 out of 16. That's weird, right? We have a shader with a maximum achievable occupancy of 16 out of 16, yet it's running at below 25%. The answer actually lies in the red box here. It says total wavefront 510. Let's run some napkin math. So if we go back again to the Overview tab and the Device Configuration submenu, we can see that we have 6 shader engines in this GPU. Each shader engine has, 2 shader array, 4 WGPs per shader array, so that's 8 WGPs per SE for a total of 48. Each WGP has 4 SIMD, so that's a total of 192 SIMDs. And each SIMD has 16 slots, which makes a total of 3,072 slots. But we're trying to run only 510 wavefronts. This is 16.6%, but it's the only reason that occupancy is not higher is just because there's not enough work to be executed. So this workload is a very tiny workload executed on a very big GPU. So if there is one thing that you need to remember from this talk is that it is always important to feed your GPU with enough work. And because I know some of you are visual learners, I made you a reminder here that you can take home with you. Be the orange cat and feed the GPU. Another usual occupancy issue that we see with RGP is a gap like this one in the red box. We have 2 workloads, one after the other, and the first one has some kind of a tail here where occupancy diminishes, and the next one has occupancy rising. It's actually the exact same thing, right? This workload, at the end of its execution, there's not that many wavefronts in flight left, right? Because the workload is ending, and so there's no work to be done anymore. And the next one has the same issue. It starts from 0. We only have a single SPI per SE, and so by the time it fills all the slots available to all the SIMDs in the SE, well, it takes a little while to rise. And if we look at the event timing tab, it is fairly explicit why that happens. we have a dispatch followed by a resource barrier followed by another dispatch. So basically, the computer graphics engineer here said, hey, those two workloads, they cannot overlap. So it instructed the GPU to force the first one to finish before the other one can start. If those two workloads cannot overlap, there's nothing you can do about this. In this case, the barrier didn't need to happen between those two. So what I did is that I moved it before, and this occupancy gap disappeared. So as much as possible, if you can overlap your workloads, please do so. That will be very helpful. If you've looked at the timeline tab at the top, you might have seen that the numbers were very, very small, and it's just because it was an example in which it was very easy for me to craft that example. But in practice, it can be much longer. So in this example, which is just one that I had on my computer, it's about 50 microseconds, which is, it's starting to get relevant, especially if you have many of those. But in practice, the tail end of a workload can be much longer. I haven't shown that so far, but workloads that overlap, they don't have to be part of the same stage. So for instance, here you can see some blue and some yellow overlapping, so that's a pixel shader and a compute shader, and that's perfectly fine. So again, for the visual learners, this is my ideal view of your workloads, if possible. I know it's not always the case. Something else that I want to mention is that so far we've seen that at the beginning of a workload, the occupancy can take a while to rise, and there's nothing you can do about it short of overlapping different workloads. But that can also happen at the middle of a workload, as you can see here. In this case, it is very likely that you are launch rate limited, which means the GPU actually retires wavefront faster than it can schedule them. So this is very likely happening if your wavefronts are very short. So if we try to describe what is happening here, it's likely that at the beginning of the workload, it takes a while for the GPU to fill all the slots. And then because it's the beginning of the workload, the caches are not primed, so it's likely that the wavefronts are stalled waiting for memory. And once they get the memory, they start executing really, really fast. And they execute so fast that the GPU can't keep up scheduling new wavefronts. And so occupancy decreases. After a while, it's likely that the caches are not prime anymore, and the wavefronts are stuck waiting for data again. And so this time, the GPU catches up, and it is able to schedule wavefront faster than they can finish. And then we're back for some more cycles. So if you're seeing this sawtooth pattern in one of your workloads, it might be worth investigating if your wavefront is really short, and if it is, maybe you can try to batch multiple items in a single thread. There's something else I wanted to mention about pixel shader, but unfortunately I don't have a good visualizations for this, so you'll have to just listen to me. When pixel shader executes, they are getting attributes from the vertex shader to interpolate them. And those attributes, they are stored in LDS. In practice, a pixel shader wavefront can actually apply to multiple primitives, which means we have to store the attributes from all these primitives to LDS. And if your triangles come with a lot of attributes, then that makes up a lot of attributes to store in LDS. And so you can be LDS, occupancy limited by LDS in a fragment shader at runtime. But interestingly, because this happens at runtime, you can't know prior at compile time if you're going to be limited, occupancy limited by LDS. So it's, if nothing else makes sense, it might be worth looking into that, checking if you have a lot of small triangles on screen, and maybe checking your lot system. Another thing that we often hear is that people don't manage to reach 100% occupancy when running geometry workloads. Well, that is perfectly fine. Usually at 50% occupancy, you already maximize the throughput of your GPU. And that is because GPUs have other limits, for instance, the number of primitives or indices it can work on at the same time. So this is pretty much fine. If you want to know more about this, we actually have another blog post on GPU Open about mesh shaders, which kind of dives a bit into geometry workloads and have a lot of tips and tricks on how to do this right. And if you've seen the work graph presentation, Max wrote some of that article. And I promise this time the commercial break is truly over. Okay, one more neat trick that we added to the Radeon GPU profiler recently is this color by limiting factor occupancy view. So it's the same view that we saw earlier with the blue, the green, and the yellow, but this time we color by which factor was limiting occupancy. So right from the get-go, you have like this view that tells you, hey, this workload is vGPR limited, while this one is LDS limited. So if you are willing to investigate occupancy, it might be a good starter point to immediately get a good idea of what's going on. Okay, we are reaching the end of this talk, so we will be trying to give you some things to go by. Does better occupancy necessarily mean better performance? I hope for everyone it is now clear that no, that's not always the case. We have shown an example where increasing occupancy wouldn't help at all, just because it's running so much ALU work. But we've also seen cases where increasing occupancy is actually harmful. When should I care about occupancy? Well, as we've mentioned before, it's whenever the GPU needs a little help to hide latency. So when a workload is fetching data from memory and waiting for it, hopefully you can schedule a different wavefront to execute some ALU work in the meantime. Does maximum occupancy mean that all the memory access latency from my shader is hidden? Actually, we haven't mentioned that before. And the answer is obviously no. If you, like me, write terrible code like this, even though occupancy here is 16 out of 16, and it's not shown here, but the measured occupancy was also 16 out of 16. Here we have a huge red bar with, I don't know, 12,000 clocks, I think, of latency, and yet I'm hiding maybe 10% of it and not even 5%. I don't know what it is. So no, the GPU is in the right place to hide the latency, but it doesn't mean that it's going to hide all of it at all. Is lower theoretical occupancy always bad for performance? Well, no. We've seen that some workloads with very low occupancy are not that bad. But actually, yes, it's probably bad. So I'm only half joking here, but I'm mentioning this because if you have a workload with a very low theoretical occupancy, it probably means that it's using a lot of resources, including vGPRs. So this is the pipeline state tab of RGP. And here we can see that this shader uses a lot of vGPRs. 144 are allocated. And there's also this toggle turned on, which says registers spilled to scratch memory. So what happened here is that the compiler decided that occupancy was so low, it was probably a good idea to offload some of the very fast vGPRs to memory to increase occupancy. But then that introduces a lot of latency, right? Fetching data from memory can be really slow, and so if it's a critical part of the shader, that could introduce a lot of latency. In practice, sometimes that helps, but if you see that kind of workload, I would encourage you to try and check out first if vGPRs were spilled, and if they were, try to figure out if that makes sense for your workload. And I think that's it. I just need to show you this copyright and disclaimer slide to make the lawyers happy. And other than that, I just want to say thank you to the people who organized the conference. I had an amazing time today. I want to thank my colleagues at AMD for teaching me all that. And then also I want to thank you for joining. Please, if you have any question, do not hesitate to ask them now or send me a message at work or on my socials.
Hello, great presentation.
Thank you.
I was wondering, you mentioned that shaders with a lot of texture accesses and high wavefront occupancy can potentially cause performance issue. Is there a tactic for reducing occupancy if you need to do so?
Sorry, can you repeat that again with the mic a bit closer to your mouth?
Yeah, sorry.
No worries.
You mentioned that there is potential performance problems with shaders with high amount of texture access and high occupancy. Is there a strategy for reducing the number of wavefronts if you feel you need to do so?
Legit strategies? No, not really. You don't have any control over this, unfortunately. I've heard of people introducing VGPR bombs. I wouldn't recommend it, but it's possible.
Thanks for a great talk. Could you still elaborate a little bit more on the differences between wave 32 versus wave 64?
Sure. No, it's going to be hard to have an exhaustive list of things that changes. But one thing that comes to mind, for instance, is that all the operations that are executed on the GPU, they're usually pipelined. Like the SIMD that we mentioned, when I say something executes in one clock, it doesn't really execute in one clock, right? It's a pipelined operation, so in the end, one operation per clock retires. Which means that if you're doing two operations one after the other, and they depend on one another, then you will get some kind of a bubble in the pipeline. In Wave 64, since you have to execute each execution twice, because the SIMD is only 32 wide, so if you do the first part of the Wave 64 and then the second part, you kind of reduce this bubble. So that's one of the advantages that you can have with Wave 64, for instance. But I know it's a topic that a lot of people are interested in, so I actually need to write a blog post about it and hopefully give you a more exhaustive answer.
All right, thank you.
Hi, thank you for the talk. I want to ask, do you have any link between thread group sizes and wave sizes? And if there's no LDS, if there's no group share memory, what's your thought process behind choosing one?
I'm not sure I understand the question. You're saying if I don't use LDS, what's the...
Yeah, so you're writing a compute shader that doesn't use any group share memory. Let's say your wave size is 32. How do you choose the group size?
Well, it really depends, I guess, on what you're willing to do with your workload. I don't think I have a one rule for everything, and it kind of depends on the GPU as well. I would advise to just profile and see what happens.
Yeah, that's proven effective. Thanks.
Yeah, I mean, it really depends on the kind of workload that you're running. For instance, I think Sebastian Aaltonen has a great blog post on GPU Open on using large thread group size. If you're doing simulations with an island, then you might want to limit the outskirts of the island, that kind of thing. But really, without a workload to tackle, it's really hard to say.
Thank you.
Yeah.
Okay, I think that was the last question. We have a break now. And okay. I think it will be coffee / water, juice. So a short break, and then we come back here for the last presentation.
Thank you very much.